So we're going to finish up a couple of problems for applications of the logarithmic or exponential equation. And so again, an exponential equation is P e to the RT, where this stands for your, P stands for your initial amount. E is the number, E, it's the Euler number, 2.718, kind of like pi, it's an irrational number. Defined it earlier in a different video. T is time, and R is your rate of growth or decay. And so that just kind of gives you an idea of what everything means there. Y would be whatever we're after, whatever our final amount is after a certain time t. And again, you're going to be looking at an equation that looks something like this if it's growth, the opposite if it's decay. So suppose you have 600 grams of a radioactive substance that are present initially, and 3 hours later, or 3 years later, you have 300 grams remaining. Yeah, 3 years later, you have 300 grams remaining. So, in other words, we've went our half-life is 3 years. So, you could definitely answer this question pretty quickly. But I'll show you how to do it with and you can logic it out in a hurry too. But I'm definitely going to just show you where everything would go. So your initial amount is the 600 grams. And so you'd have, and 300 is your final. So your equation looks like this. So we're going to end up with 300 grams. We started with 600. It's going to be E. We don't know our rate of decay. And our time t is after 3 years. So that gives you the rate of decay per year. So this model will work to find your half-life. And so if you solve this thing, you would divide by 600 to get that Euler number by itself. And so you'd have 1/2, it's 300 divided by 600 to half equals e to the 3r, just to kind of rearrange that. And again, anytime you have an exponent that you're solving for up here, you can just natural log both sides. And what happens is that 3r will pop to the front. And so you'd have ln of 1/2 equals 3r ln of e. Well, the natural log of e, you can plug it in if you want, that'd be e to the first. That is 1, so that's gone. Natural log of 1/2 is negative 0.69, just rounding it, 315 is approximate, equals 3r. And so then you can divide by 3. And that'll give you your rate of decay. So our rate of decay in this particular problem is negative 0.23105. And so that's what our model would be. So to find any amount of radioactive material, you could just use this model times t. And so that is your model that we're after for any amount. So now when you do part B, you can just plug in that 6 years. So this would be y equals 600 e to the negative 0.23105 times 6. And you'll get approximately 150 grams, or whatever units we had started with. So after 6 hours, we would have 150 grams. Now that should make sense because in 3 hours we had half the material left. So 6 hours is another 3 hours. So half of 300 is 150. And so it should make sense for that part of it. All right. So that's the first problem. Second problem, again, they're all very similar. And so this next problem is a little tougher. Newton's law of cooling. So, Newton's law of cooling, anything cools, you stick a hot cup of coffee on the desk, it's going to cool at this rate. And you can see the same PERT here. The only difference is you've got that T sub naught there, which is the initial temperature of the environment. So T sub naught is your initial temperature of the environment, or the temperature of the environment. C would be your initial temperature of your object, whatever your coffee, whatever you're putting out. And then K, they have a K here, but that's your rate of decay. And then T is time in hours. And so our model to fit this data would look something like this. It would be, you've got 100 degrees coffee. We're going to sit down in a room with a temperature of 20 degrees. So we're going to have F at T equals 20, because that's your temperature of your room, plus your initial temperature is 100 degrees. E, that's supposed to be an E, there we go. E to the, we don't know the rate of decay, so we'll go minus K. And then T is time. Well, it says the coffee is 60 after 1 hour, so that's going to be a 1. And then this F at T, you could put a 60 in there. And so we're going to be solving this. 60 equals 20 plus 100 E to the negative K. And so you can solve this thing for K now. So, just start cranking it out here. You'd subtract 20. So we want to get that K by itself. So you'd have 40 equals 100 E to the negative K. You'd have to divide by 100. So E to the negative K. And so 0.4 equals E to the negative K. And again, you want to natural log both sides to get that K to pop out front. And so you'd have natural log of 0.4 equals negative K. I'll try to write it legibly. ln of E. And again, that ln of E is 1. So it's gone. And so K then is going to be the negative natural log of 0.4. And so if you plug natural log of 0.4, and I should keep the negatives in here, just not make them disappear, is negative 0.91629. And so you change your signs, and K is 0.91629. So our model for our particular problem is going to be F at T equals your initial temperature, or your room temperature, which is 20, plus your coffee temperature, which is 100, E to the negative 0.92 T. Had to squeeze that in, and you could use it as as many decimals as you need. We're probably just getting approximate temperatures, so you don't need a whole lot. Not after any nuclear physics stuff here. Just temperature of coffee. And it says find the temperature after a half an hour. So you just put in 0.5 to this model. So this would be F at T. I'll try to squeeze it in here so it fits better. F at T equals 20 plus 100 E to the negative 0.916 times 0.5. And you just get a calculator out and type that thing in. And I encourage you to do that. Make sure you know where that stuff's at. And so after half an hour, you should get approximately 80, if you type all that in, you should get approximately 83 degrees, approximately. And then for part C, how long will it take for the coffee to cool to 50 degrees? Well, again, we can go ahead and just plug 50 degrees into this thing. So 50 equals 20 plus 100 e to the negative 0.916 t. And we're going to solve that equation for t. So you would subtract 20, and 30 equals 100 e to the negative 0.916 t. Then you would divide by 100, and 0.3 equals e to the negative 0.916 t. And then you would natural log both sides. So you'd have a natural log here, you'd have a natural log there. And you got natural log of 0.3 equals negative 0.916 t. And again, ln e, which is 1. So then you just divide by the negative 0.916. Supposed to be a decimal there. Negative 0.916. And that will give you about 1.3 hours. And so just move it over to get myself just a little bit more room. And so what we do is, I mean, that's it. You just type this in. So it's our answer for time t is approximately, just to write it up here so you can see it at the top of the screen, divided by negative 0.916, approximately. So time, I've got a little bad spot in my smartboard there, 1.32. So, and there you have it. There's some exponential functions and how to solve them and how to model them. I hope this helps. So pretty soon you can start doing inflation and all kinds of other calculations on your own if you're wanting to know those values for yourself instead of relying on somebody else to tell you how to do them. See you next time. Hope this helps.